Okay, I wanted to talk really briefly about logarithms, about logarithmic functions and exponential functions, and how to solve equations involving those. Again, this is very brief. You'll need, if you need more extensive help, please let me know. Main thing to remember, logarithms are exponents, all right? If we have 3 to some power x, and that's equal to 31, then we say the logarithm, or log for short, base 3. Okay, so the 3 comes from the base here, 3 of 31 is x. So the logarithm of 31, the logarithm is x. Notice x is the exponent. So we are taking a logarithm, we're finding the exponent on the base. So the base depends on the base for sure. To get this value, in this case 31. So for example, log base 2 of 16 is 4 because the base 2 to that 4th power, that logarithm, is 16. Right? Since 2 to the 4th power, 2 times 2 times 2 times 2 is 16. Log base 2 of 16 is 4. Log base 3 of 1/9 is -2. Why is that? Because 3 to that logarithm, to that power, -2 power, is what? The same as 1 divided by 3 squared, which is 1/9. Log base 7 of 1 is 0. Why is that? Because 7 to the 0 power is 1. Log, now what is log without any base? What do we mean there? This is sometimes called the common logarithm. It is the same as the log button in your calculator down here, for instance. That is base 10. In fact, when you look at the calculator, you'll see log, and then the shift function or second function is 10 to the x it takes. So it's the corresponding exponential function. So log is base 10. So log base 10, or log 1000, is 3, again, because the base in this case being 10 cubed, 10 times 10 times 10 is 1000. ln, that is log base e. And we use this abbreviation ln for logarithmic natural, which is the French rendering of that. So we take the natural log of e to the 7th power, we get 7 because e to the 7th power is e to the 7th power. All right, the ln function is on the calculator there, and of course you can see it's connected to e to the x, so that reminds you that the base is e. Those are the two most prevalent logarithms we use, and probably the natural logarithm being the most important one. But this last situation here illustrates the important relationship that exists between exponential and logarithmic functions. So let me just briefly give you the rundown of those two types of functions. For any base a that's positive and not equal to 1, this is the exponential function with base a. Right? Notice we're inputting to this function an exponent. So a is some real number that's positive, not equal to 1, and we plug in exponents on that base. The domain of such a function is all real numbers, and that means I can take any real number to any exponent, be it positive or negative or fractional, right? Like to the 1/2 power would be like the square root, for instance. The range of this function is everything greater than 0. I cannot get an output of 0, right? The base is positive. Therefore, any positive base raised to any exponent will never be 0, and of course, never be a negative number. The y-intercept is 0, 1, and if I take any base and raise it to the 0 power, I get 1, and that's why we always have this ordered pair, 0, 1, for this function. We have a horizontal asymptote of y equals 0. The corresponding inverse function, because in fact the relationship is that they are inverses of one another. So the inverse of the exponential function of base a is the logarithmic function of base a, and vice versa. The domain of the logarithmic function is everything greater than 0. Notice it matches the range of its inverse, and the range of the logarithmic function of base a, all real numbers, which matches with the domain of the exponential function. We have an x-intercept of 1, 0, and that's because log base a of 1 is always 0. We did a specific example here. Log base 7 of 1 is 0, but if I picked any other base, any other number, I would still get 0 because any base raised to the 0 power is 1. We also have a vertical asymptote of x equals 0. So again, y equals a to the x if and only if log base a of y is x. So they cancel each other out. They're inverse functions. If I take x and plug it into the exponential function and get out y, I can take y and plug it into the logarithmic function of base a and get back to x. They cancel each other out. So we use those relationships, for instance, when we're solving equations. So the graphs of logarithmic functions and exponential functions depend on the value of a. If a is greater than 1, the exponential function is increasing on its domain, as is the logarithmic function. Notice we have a horizontal asymptote as x goes to negative infinity. The exponential function is approaching 0. So we have a horizontal asymptote of y equals 0. And the logarithmic function has a vertical asymptote as x gets closer to 0 from the positive side, it's going to minus infinity. And also you'll notice that for inverse functions like this, if we draw the line y equal x, which is just a line of slope 1 passing through the origin, then these graphs are reflections about that line. All right, and that's true for any inverse functions. If the base is between 0 and 1, then the graph of the exponential function looks like this. It's decreasing on its domain, and it's approaching the horizontal asymptote this time as x goes to positive infinity. And the logarithmic function of base a in this case is decreasing on its domain, and as x approaches 0 from the positive side, it's going to positive infinity. Still have the same horizontal and vertical asymptotes respectively. So again, in particular, the exponential and logarithmic functions have this inverse relationship. Log base a of a to the x is x because they cancel each other out. And if you think about just what this is saying, logarithm is the exponent, right? What's the power on the base a needed to get a to the x? A to what power is a to the x? Answer x, right? That's by definition of a logarithm. But they cancel each other out here. A to the log base a of x is x. Again, they cancel each other out. Log base a of x is the power of a needed to get x. So if I raise a to that power, I get x. In particular, if I use base e, right, which would be ln, natural log of e to the x is x, and e to the natural log of x is x. And so, for instance, we have these situations. Log base 4 to the 13th power is just 13. 7 raised to log base 7 of b is just b. The natural log of e to the 10th power is just going to be 10. And e to the natural log of 4 is 4. So these are important relationships that you should recall from your study of exponential and logarithmic functions. Now, in particular, solving, say, exponential equations, there's many types, but here's a basic type, right? We have an exponential expression. What we want to do is isolate that exponential expression. Okay, so I'm going to add 4 to get 19 here. I'm going to divide by 3. And then how do I solve? I can't like take a square root or you know, anything like that. It's not like if I had x squared equals 19/3, I would take the square root, right? But this is e to the 2x. How do I undo that? I take the natural log of both sides. And the natural log of e to the 2x is just 2x. That's that inverse relationship, right? We just talked about. And so 2x is the natural log of 19/3. I can now divide both sides by 2 or multiply by half, and I get x is 1/2 natural log of 19/3. This is the exact value, and a lot of times you might be asked to give an exact value with fractions and so forth and logarithms, and that's the way you'd write it. I mean, that's the exact value. You can, of course, approximate with your calculator, and I've done that calculation here, 1/2 natural log 19/3, and then round it off, we get that expression. But and you can also check, by the way, your equations. Say this is my estimate. If you remember in the calculator, if you use the answer ANS, if I do second ANS, right, the value of the answer is this value that was just computed. And so if I hit enter, I just get that same value. So if you want to check, notice I can plug in answer this unrounded value into this equation. So I can do 3 times e raised to the 2 times, and I'll just do answer, right? And then I'll subtract 4. Notice I've come down out of the exponent there. And so this should be equal to 15. And indeed it is. So there's a confirmation checking my work. Okay. Now, logarithms have some important properties. You should recall the log base a of a product of 2 values or functions, u and v, is the sum of the individual logs of those. So why is that? Okay, well, if u is, say, a to the x and v is, say, a to the y, then log base a of u is what? X, right? Remember, logarithm is the exponent on the base needed to get, in this case, u, which is I'm calling x, right? And similarly, log base a of v is y. Now, what is u times v? Well, u is a to the x, v is a to the y. How do we multiply like bases to different powers or different exponents or different logarithms? We add them, right? A to the x plus y. And so log base a of the product uv, what's the exponent on the base a needed to get uv? Answer x plus y, x plus y. But x, remember, is log base a of u, y is log base a of v. So in other words, right, we're dealing in the exponent realm. If I'm multiplying like bases to different powers, what do we do with their exponents or logarithms? We add them. Okay. Similarly, you can say what log base a of u divided by v is log base a of u minus log base a of v. So we subtract exponents, right? When I'm dividing, right? If I had a to the x divided by a to the y, that would be x minus y for the exponent. And then by repeated application of number 1, we get log base a of u to the n power is n times log base a of u, because this would be u times itself n times. Making repeated use of this, I would be adding n log base a u's together. So we kind of think about this last property as kind of like bring the power down in front is the way we remember it when we take the logarithm. So for example, the natural log of 4x squared, I'll make use of that first property, right? Because I've got 4 times x squared. So this is natural log of 4 plus natural log of x squared. And then natural log of x squared, I can use this property, bring that 2 down in front, and I get natural log of 4 plus 2 natural log of x. So this would be expanding the logarithmic expression. And there are times when we want to be able to do that in this course. Log of x cubed y over z to the 4th. Well, first of all, I have a quotient. So by that second property, the quotient I'll write is the difference of logarithms. So log of the numerator minus log of the denominator. And then here's a log of a product. So I'll break that up into the sum of the logs by that first property. And then I'll bring down these powers, 3 log x, and bring this 4 down in front, minus 4 log z. And there is the expanded form of that logarithmic expression. Now, with that, let's finish with just briefly logarithmic equations. Again, a lot of different forms that we can encounter with logarithmic equations, but here's some basic ones. Log base 3 of x plus 7 is 2. The trick here, since you have a single logarithm, equals 2. Remember what a logarithm is, it's an exponent. So I'm going to write it in exponential form. The base is 3. The logarithm or exponent is 2. So 3 squared is going to give me x plus 7. That means 9 is x plus 7, or x is 2. Okay, so that's pretty simple. Now, a little more complicated one. Log base 6 of x minus 4 plus log base 6 of x plus 1 is equal to 1. What I need to do is I need to get a logarithm of a single quantity. So I'm going to combine these two with the properties of logarithms we just looked at, but we're going to go in reverse. In other words, I have a sum of logs, so that must be the log of the product, right? We sort of went in the other direction previously, but now we're combining, instead of expanding, we're combining as a single logarithm of a single quantity, right? So we get this, and then I write in exponential form. The base is 6, the logarithm is 1, so 6 to the first power gives me this x minus 4. times x plus 1. And now 6 to the first power, of course, is 6. I can FOIL this out. I get x squared minus 3x minus 4. And now it's just a quadratic equation to solve. How do we do that? Set it equal to 0. Subtract 6 from both sides. So -4 minus 6 is -10. And then I can factor this, it turns out, right? X minus 5 times x plus 2. So either x is -2 or 5. Now, we always want to check our solutions, especially with logarithmic equations, because we can reach some extraneous solutions. In other words, -2 is not a solution. And the reason is, if we go back to the original equation, for instance, if I plug in -2 here, -2 minus 4 is -6. You cannot take the logarithm of a negative quantity and get a real output. And so that would not be a solution. And obviously not here as well, right? If I plug in -2 here, I get -1. Log base 6 of -1 is not a real number. The other solution was 5, and that works. So 5 minus 4 is +1. 5 plus 1 is +6. So we can do that. And of course, log base 6 of 1 is 0. Log base 6 of 6 is 1. I get 0 plus 1, which is 1. It satisfies the equation. So the only solution to this equation is x equals 5. Okay, there's certainly a lot more to this, but this hopefully will get you going and help you with any of the homework that might encounter some of these type problems. Again, as always, let me know if you are in need of help.